Hello everybody, this is the start of Chapter 5, Section 3, and we are going to be looking at periodic properties as they're related to electron configuration. We call these the trends within the periodic table. We've got 5 trends that we're going to look at today, and before we even get started, the very first thing I'm going to want you to put in your notes is going to be a chart to show period and group trends within the periodic table. Obviously, you need to be looking at a periodic table today as we go through some of this stuff so that you can follow along. But let's get to the chart. So this is the start of the chart. Again, we've got 5 trends we're going to look at, so leave yourself plenty of room to write out these 5 trends. We're going to look at the trends as we move across a period. So periods are rows, and it's going to be left to right across a period. And then for group trends, it's always top to bottom or moving down a group. So across a period, left to right, moving down a group, and those are the trends we're going to look at. I'm going to go ahead and put in here abbreviations for the 5 things we're looking at today. They are atomic radius, which we call AR, and all of these trends are either going to be increasing or decreasing, and you'll have to come back to this chart and fill it in. I may not come back to it within the podcast, but you will be coming back to fill it in as you go. After atomic radius, we are going to be looking at ionization energy. We call that IE, ionization energy. The third thing that we will look at today is electron affinity, so EA. The fourth is going to be ionic radius. And the last one that we will look at is electronegativity. Again, with each of these, you will come back to put in increasing or decreasing for their period and group trends, respectively. This particular lesson is going to be a watered-down version of the trends. At this point right now, I am more concerned with you knowing what the trends are, being able to do a little bit of application, but as far as truly why the trends trend the way they do, I'm not going to go into a lot of detail. You'll be able to tell in the background of the PowerPoint it goes into detail. I will highlight the important things you need to write down, especially definitions, and obviously anything I write in addition to what's on the PowerPoint, you need to write in your notes. So starting off right here, we've got atomic radius. So atomic radius is defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. So again, you got to have 2 atoms bonded together, and then you take the half the distance between their 2 nuclei. The reason why we do that is because, and it tells you up there above it, the edge of an atom is very fuzzy. You've got your electrons that are moving super fast in a wave-like motion, spinning on their axis. So because of that cloud-like edge that you have to atoms, we do bond 2 atoms together and take half the distance of that bonded diameter that you have. So that is atomic radius. And the trends for atomic radius, again, it does go into a lot of detail about why they trend the way that they do, but we're going to look at the actual trends themselves. So it gets smaller across the period, smaller, that would be decreasing. And as you move down a group, they get larger, so that is increasing. So I want you to go back in your chart right now that we started off with. And for atomic radius, you're going to put under the period trend, you are going to put, I'm trying to change my ink color here. Under the period trend, you are going to put decreases. And under the group trend, you are going to put increases. So the size of an atom gets smaller as you move across a period, gets larger as you move down a group. This right here is showing you those trends. We're going to look at just the top chart. I notice that you have a lighter green up there at the top. So lighter green here gets small, darker green, it gets much larger. So those are your period trends. Let's go apply this to an example. Again, you're looking at your periodic table, and you're finding magnesium, chlorine, sodium, and phosphorus, and it wants to know which has the largest atomic radius. When I get to problems like this, the first thing I'm going to do is I'm going to draw me a fake periodic table, and I'm going to label where these particular elements are actually located. I'm going to erase a little bit of this because I know that I need that to be a little bit larger. And the elements that is asking about here, I'm going to find sodium and magnesium. I know on the periodic table they are close together. Sodium, magnesium, and then it says phosphorus and chlorine, and it wants to know which has the largest atomic radius. Well, we just looked at atomic radius, and atomic radius, as you move across a period, we said it gets smaller. So I'm going to put a small box right there, meaning small. And we said as it moved down a group, because we always start in this area here, as we move down a group, they get larger, so expect your largest ones to be right here. So I'm looking where I have the small and the large box, and I'm going to look at the 4 examples, and it says which has the largest atomic radius. Well, which one is closest to the large box? The one closest to the large box is going to be sodium. So of the 4 that we have here, sodium is going to have the largest atomic radius. We're going to see other examples like this with some of the other trends, and you will see every time I will draw a fake periodic table, I will label the elements in question, I will write out where does my small box and large box go, because depending on the trend, those 2 boxes could be in the opposite corners. And then I'm going to answer the question, what's the biggest or smallest, with the elements that are presented. Next, we're moving to ionization energy. Several more definitions. Definitely get your definitions here. An ion is an atom or group of atoms that has a positive or negative charge. Positive or negative charge. We have names for these, which we're going to hit here momentarily. But a cation has a positive charge, and an anion has a negative charge. Next up, after ion, you have ionization. And ionization is a process that results in the formation of an ion. And then we're going to look at ionization energy, because ionization energy was the second trend we're going to look at. Ionization energy, it is important to know that it is the energy required to remove 1 electron from a neutral atom. So we are removing an electron from a neutral atom, and energy is required to do that. Now, for ionization energy, the trends that we're going to look at here, again, it goes through the details of why they have the trends that they do, but I want you to know the trends themselves. So ionization energies increase across a period, and ionization energies decrease down a group. So please go back to your chart from the very beginning. For IE, the period trend is increasing, and the group trend is decreasing. Now let's go work out an example. Everything here is written down, so I have gone through, made up the periodic table. I have labeled the S&P block. I did my large box and my small box with the respective numbers based on the ionization energy trends, and it's asking me which element is more likely to form a positive ion. Well, you've got your cations and your anions. Cations are what make positive ions. Based on ionization energy, this is which one would it be easier to lose an electron, because cations will lose an electron through this ionization. And the one that requires the least amount of energy will form a cation because it will be losing the electron much easier. Our final answer on this one is going to be the one that is in the S block. Please make sure you've written all of this down along with the example so that you can process all the little details that are within it. Moving on now, we're going to, this is again explanations to it. Now moving on to electron affinity, which is our third trend. This one is wrapped up pretty much in just one slide. So electron affinity, its definition. Again, another energy change that occurs when an electron is acquired. Acquired means gained. So an electron is acquired or gained by a neutral atom, and it's the energy change involved there. So if an atom gains an electron, it becomes negatively charged or becomes an anion. So again, anions have a negative charge. We have acquired or gained an electron. And the trends that we have for it are increases across a period. And again, this is generally, and decreases down a group. So please go back to your chart. And for electron affinity, make sure you put increases under the period column and decreases underneath the group. We have a lot going on in this slide, but it is our fourth trend called ionic radii or ionic radius. Radius, again, is going to be the size that you have. We've already done atomic radius, which was the size of a neutral atom. Well, now, what's the size if your atom has gained or lost electrons? You do, again, have a lot of writing. So, again, a positive ion is known as a cation. So they have lost one or more electrons. So with the loss of an electron, the electron cloud does become smaller. So expect your cations to be smaller than the neutral atom. Okay, electron or the cations will be smaller than your neutral atom. And then we have our anions. Anions are negative ions. That means they have added one or more electrons, and they will increase in size. So an anion has a negative charge because it has gained one or more electrons, and an anion will be larger than its neutral atom counterpart. The trends for ionic radius are the same as those for atomic radius, and for the same reasons. So ionic radius does decrease across a period, and it increases as you move down a group. So please add those trends to your table. Again, period trend decreases, group trend increases. And again, that is going to be the same for atomic radius or ionic radius for the same reasons. Next up, we have valence electrons, and you've already heard this term before. So the definition for valence electrons, the official definition, is electrons available to be lost, gained, or shared in the formation of a chemical compound. Again, these valence electrons are going to be the ones typically at the highest occupied energy level. So we have talked about that. In your S and P sublevels, so highest occupied energy level in your S and P sublevels. And it also says your valence electrons are often located in incompletely filled main energy levels. We're talking about main group elements for the most part. That's what we're going to concentrate on. So let's go look at a chart that I'm going to want you to add, talking about valence electrons. Again, since we're concentrating on the main group elements, that's the S block, which contains groups 1 and 2, and the P block, which contains groups 13 through 18. Our generic or group configuration for these, as seen earlier in the chapter, there is your ending configurations if you're talking about the S block. And for the P block, we said you have to go through the S block to get through the P block, or to the P block. So I'm going to go ahead and fill in this part right here. And then we're going to go back and we are going to add some number for the different groups within the P block. So again, within the P block, there are 6 actual groups, since it's groups 13 through 18. So there are 6 options to which electrons are going to add for the P block. So if it's the first group in the P block, it's P1. If it's the last group in the P block, it's P6 for your group 18. If you count up the number of valence electrons, because this is the important part, it looks just like this. So you have 1 through 8 valence electrons, group 18. Always talk about the happy 8 or your octet. And we are looking at having 8 valence electrons. We know group 18 is very stable. Those are our noble gases, and other elements want to be like your noble gases. So what can they do to be like a noble gas and have those 8 valence electrons? Let's also go look at a periodic table version of this. So if I have my periodic table and I've went ahead and labeled the groups 1, 2, and 13 through 18 for our S and P block, the number of valence electrons that we have, group 1 is 1, group 2 is 2, and then we jump over, group 13 is 3, and again that goes all the way up to 8 valence electrons for group 18. Helium is within group 18, but we know helium is technically part of the S block and is filled up with 2 electrons, which are also both valence electrons. So they will not have 8. But the rest of your noble gases over here within group 18 will have 8 valence electrons. And what we're going to look at now, because you will have some questions that you'll have to run across here and there, is what do your different groups need to do to become stable like your group 18? Would they lose or gain electrons? And ask yourself what sounds like it would be easiest to do. If group 1 has just 1 valence electron, it sounds to me like if it just lost 1, instead of trying to gain 7 more electrons, it could be a lot like group 18. Same for group 2. It has 2 valence electrons. It could lose 2 instead of trying to gain 6 more to get to 8. Group 13 would lose 3 instead of trying to gain 5. Group 14, it has 4, so is it going to lose 4 or gain 4? It'll go both ways. Once we get to group 15, it already has 5 valence electrons, so instead of trying to lose 5, it would be easier to gain 3 electrons. 5 plus 3 is 8. Group 16 already has 6, so it'd be easier for them just to gain 2 more. Group 17 has 7 valence electrons. It'd be really easy for them to gain 1 more valence electron. And then again, group 18, they're not going to do anything because they've already got a stable configuration. Now, remember, losing and gaining electrons, what does that do for your charge? Well, if you lose 1 electron, that means you lost a negative. So you're going to have a 1 minus charge. For group 2, if it loses 2 electrons, it's going to have a negative 2 charge. Or sorry, both of these are positive. My bad. Positive. Because they're losing electrons. If I were to look at, say, beryllium, for example, that has 3 protons, 3 electrons, and beryllium has 2 valence electrons. If it lost 2 electrons, just like this, notice you have 2 positives that have no other charge to balance those out. That's why it would be a plus 2. So moving on over to group 13, if they lost through 3 electrons, they would have a positive 3 charge. And then when we get into gaining electrons, again, you've gained your negatives. So if it gains 3, that's a negative 3. If it gains 2, gains 1. Those are going to be the respective charges within each of those groups. A lot of information on this slide. Please make sure you get all of this down. Very, very important. And the last trend we have is dealing with electronegativity. Here is the definition for electronegativity. It's its ability of a compound to attract electrons from another atom in a compound. So we were talking all about, can I attract electrons? The trends that you have for electronegativity, they increase across a period and decrease as you move down a group. So please go back to your original chart and make sure you get increases across a period and decreases as you move down a group, and that will fill out that original chart that you had. For our electronegativities, I do want you to add a couple of things here. Your most electronegative group is going to be group 17. Group 17, if you recall, they already have 7 valence electrons and they just need 1 more electron to gain to get to stable 8, so they have a high attraction for electrons. Whereas your least electronegative group is going to be group 18, because group 18, again, is already stable. And your most electronegative element, and this will come up multiple times this year, most electronegative element is fluorine, and it has a value of 4. So the electronegativity value for fluorine is a 4.0, and if you were to look at values for all of the atoms or all of the elements, they're going to be between 0 and 4. Working off of a sample here, and we're going to work this one out the same way we've done the others. They've given us gallium, bromine, and calcium, and it wants to know which one has the highest electronegativity. So I am going to make my fake periodic table again. And with this periodic table, I'm going to put the small box and the large box. Electronegativity trends. We said the trend for electronegativity increases as you go across a period, so I would expect a large box in this area. Again, fluorine is in that area, so highest electronegativity value is fluorine, and as you move down a group, the trends become smaller. If I label these 3 elements and where they are at, we've got calcium over here, we've got gallium here, we have bromine right there generally. So the one with the highest electronegativity is going to be the one that is closest to the largest box, which is bromine. So I'm going back showing you this chart again. Notice I've rearranged mine because as we were going through it, I did say that both of our radiuses, atomic and ionic radius, have the same trend. And the other 3, hope you notice, they have the same trend. So for atomic radius, they decrease across the period, increase as you move down the group. And for the ionization energy, electron affinity, electronegativity, all of those increase as you move across the period, and they decrease as you move down the group. So this should be super easy memorization. Make sure that you get all of this memorized so that you can apply it.